coming to the discovery of electron. See, electrons were discovered by J.J. Thomson. But before that, you know, Michael Faraday, who actually was studying on electrolysis during his experiments on electrolysis. You know, electrolysis is a process of decomposing an electrolyte, like for example, sodium chloride, by passing the electricity. Okay. Okay, the process of decomposing an electrolyte by passing electricity. And I've got some more interesting points to discuss here. You know, electrolysis is carried out in an apparatus called electrolytic cell. Okay, now it will be the same as this. Come on. Now, this is actually called a cathode ray discharge tube. Using this, Michael Faraday was actually studying about electric discharge. I mean, the process of decomposing electrolytes by passing electricity. Now look at the electrodes that are here. You know, there is cathode and nothing but a negative electrode. This metal piece, what you can see here, is the negative electrode. It is called cathode. And see this. This is a positive electrode and you know it is called anode. So this is about the electrolytic cell, which consists of course, two metal pieces called electrodes. Okay. So this cathode ray discharge tube is of course made of glass. Okay. It is made of glass. And see, in order to carry out the electric discharge, of course, a gas is filled in this. Now, this gas is subjected to electric discharge. I mean, electricity is passed, let us say. Look at this. It is passed through the two terminals, cathode and anode, through terminals. Now, when this gas is subjected to electric discharge, you know, under low pressure conditions, the low pressure, yes, of about 0.01 mm of mercury pressure is used. At the same time, high voltage is also used. You know, these are the conditions at which the electrolysis or electric discharge is carried out. The low pressure of 0.01 mm of mercury and high voltage of about 10,000 volts potential is applied. So the conditions required for the generation of electrons are low pressure and high voltage. Okay. Next. What happens when the gas is subjected to electric discharge? You know, when it is subjected to electric discharge, the negatively charged electrons flow from, because they are negatively charged, they'll be moving towards positively charged electrode. So electrons will be moving from cathode to anode. Let me just show you. So this way they'll be flowing through. Okay. In this way, current starts flowing in the form of stream of particles which move from cathode to anode. See, because electrons are negatively charged, because they are negatively charged, they are moving from cathode to, of course, anode. Cathode is negative electrode and anode, of course, is a positive electrode. But how to know whether they are going from cathode to anode or from anode to cathode? Yes, that can be known using a zinc sulfide coating. Zinc sulfide is, of course, phosphorescent. You can also use some fluorescent substance, because when you go for a fluorescent substance, as and when the electrons fall on the coating, you get a kind of scintillation. Now this zinc sulfide coating is used in order to know whether electrons are moving from cathode to anode or from anode to cathode. Yes. See, when a zinc sulfide screen is placed, by making some holes, look at the holes in the anode, this plate, when some holes are made and when the electrons are allowed to move through the holes and are allowed to fall on the zinc sulfide coating, you know, you get some scintillation. A bright spot can be seen on the zinc sulfide screen. You can just see the bright spot. Okay. So that is how they came to know that the electrons are negatively charged. Because they are negatively charged, they move from cathode to anode. They move towards anode. The same kind of thing happens even in case of television set. As and when the rays fall on some kind of a coating, we get the picture. The bright spot or the bright picture can be seen only when the rays fall on some screen. Okay. So this is what was actually done during the discovery of electron. Now coming to the cathode rays. As we have seen, cathode rays consist of negatively charged electrons, right? They consist of negatively charged electrons. Next, of course, they are invisible. You cannot see them. You can only see them using certain material like zinc sulfide screen, what we have used now. Next, you know, these rays travel in straight lines. In the absence of electric and magnetic fields. Of course, in electric and magnetic fields, they travel in different ways. We'll show you that later. Okay. Now, the most important thing is whatever the gas filled up in the discharge tube, of course, you get the same kind of electron or you get the same kind of cathode rays. That is the most important one. You know the characteristics of a cathode rays is independent of the gas filled in discharge tube. Whatever may be the gas, you get electrons of the same type. So this is very important. Independent of the gas filled in the discharge. Okay. This is all about the discovery of electrons. Cathode ray discharge tube was in fact constructed by Michael Faraday for his electrolysis studies, but was actually used up by J.J. Thomson in discovering the electrons. So electrons were of course discovered by J.J. Thomson. The name electron was given by G.J. Stoney. The conditions required for getting the cathode rays are low pressure and high voltage. So these are the important points. Now, let us go for charge to mass ratio. That is E by M. Let me just okay. This is what I want. Now coming to charge by mass ratio. Electrical charge by mass, nothing but E by M ratio. This was also discovered by J.J. Thomson. Okay. Coming to this, you know, looking at the picture, it gives you clear information about the usage of two different things. Look at this. This is the electric field applied. Right. Now, how about this? This is the magnetic field applied. Electric and magnetic fields are perpendicular to each other. And if you see the path of electron, even that is perpendicular to these two. Electric and magnetic fields are perpendicular to each other. Of course, even perpendicular to the path of electron. Look at this red one, referring to the path of electron. They are moving from cathode to anode under the influence of electric and magnetic fields. Okay. Now again, a fluorescent screen is observed in order to know whether anything has hit the screen or not. Okay. You get a bright spot if something hits the screen. If not, you get nothing. Now here you can see the points A, B, and C. Now this is the actual path in which the electrons are moving. They are moving in straight line. But see, because you have applied electric and magnetic fields, right up to this, they are moving in straight line. But when electric and magnetic fields are applied, see, their path has changed. Okay. If you check what happens when only electric field is applied. Only electric field is applied. You know, the path is going to be A. Path A is adopted or path A is followed when just electric field is applied. Similarly, when only magnetic field is applied, you know, path C is adopted. Right? Path A when electric field is applied, this. Path C when only magnetic field is applied. But you know, by carefully balancing electric and magnetic fields, it is possible to get them again onto a straight line. That is B. Of course, this B will in fact be the path followed when there is no electric and magnetic field. But here we are using electric and magnetic fields, but still we could actually get them onto straight lines by carefully balancing electric and magnetic. So that is the interesting part. Now, what are the factors on which the deviation, the magnitude of deviation of electrons or the cathode rays depends? It actually depends on three things. The first one is the magnitude of negative charge on the particle. Coming to the magnitude of negative charge. Greater the negative charge on the particles, I mean on the cathode rays or on the negatively charged particles present in the cathode rays, nothing but the electrons. So greater the negative charge carried by the electrons, greater is the deflection. I mean, this is what I call deflection, right? So this deflection will be more if the negative charge on electrons is more. Magnitude of negative charge is directly proportional to the amount of deflection. Greater the magnitude, greater is the deflection. That is point number one. Coming to point number two, on which the amount of deflection depends, is mass of the particle. The mass of the particle and the amount of deflection or the magnitude of deflection are inversely proportional. Lighter the mass or lesser the mass, greater is the deflection, because they are inversely proportional to each other. Lighter the mass, greater is the deflection. Lesser the mass, greater is the deflection. So that is the second factor on which the deflection of the electrons depends. The other one is the strength of the field. I mean the strength of electric field or magnetic field. It's not electric field by magnetic field. Let us take it this way: electric field or magnetic field. You know, if the strength of the electric or magnetic fields is more, I mean, if say the voltage applied across the electrodes is more, I mean, if the strength of the electric field is more, or even the strength of the magnetic field is more, then of course the deflection will also be more. So the first one and third one are directly proportional to each other. The magnitude of negative charge is directly proportional to the magnitude of deflection. Even the strength of the electric field or magnetic field is also directly proportional to the amount of deflection. But coming to the mass of the particle, as I said, the lighter ones are deflected to a greater extent, right? Because they can be easily deflected. Lighter the mass of the particle, greater is the deflection. So as I said, by carefully balancing the electric and the magnetic fields, he could bring back the electrons onto the straight line. Based on these deflection experiments, what he carried out, he could actually deal with both charge as well as mass. Based on the deflection of the charged particles, I mean electrons in electric and magnetic fields, he could actually determine the value of E by M. I told you that the E by M value of electron is 1.759 into 10 power 8 coulombs per gram, or 1.759 into 10 power 11 coulombs per kg. Here the charge is in coulombs, mass is in gram. Or you can take charge in coulombs, mass in kg. Okay, this is what he could actually determine based on the amount of deflection in electric and magnetic fields. Okay. This is very interesting. Now, let us go for oil drop experiment. Yes. Look at this diagram. You know, the charge on electron was discovered by Millikan based on his oil drop experiment. This is what oil drop experiment is. Now, in this, if you observe, atomizer is used. See, they have taken oil here, and using an atomizer, they could actually get the oil droplets. You can see these yellowish ones. They are the oil droplets. They are in the form of a mist or in the form of, say, fog. They are allowed to enter through this hole, right? A small hole which is made in the upper plate. I mean the positive plate. And now they are allowed to fall. You know, the motion of these droplets was, of course, observed using a telescope. Look at this. There is an eyepiece to this telescope using which, you know, the oil drops are observed. I mean, the motion of the oil drops or the movement of the oil drops is, of course, observed. You know, the forces that are acting upon these oil drops that are falling are, you know, there is a gravitational force, of course. Any falling body will have this force operated upon it. Because you are using a positive and a negative plate, you will also have electrostatic force, because there is, of course, electric field and something called a viscous drag, viscosity. These are the forces that act upon the oil drop, right? Now, the air inside the chamber was ionized using X-rays. I mean, a beam of X-rays is passed into the chamber and the air inside is thoroughly ionized, so that there are no other electrons. I mean, there are no other things other than the electrons that are coming from the atomizer. I mean, the oil droplets that are coming from the atomizer. based on the rate of falling of oil droplets under the influence of different forces, Millikan could measure the mass of oil drop. Isn't it? Of course, if they are lighter, they'll be falling at a greater rate. If they are heavier, they'll be falling at a lesser rate, right? So based on the rate in which they are falling or they are moving, he could actually measure the mass of the oil drop. Now the electric charge on the droplet was in fact obtained by colliding these oil droplets with the gaseous ions. The ions are formed because of these X-rays which ionize the chamber. Ionize the chamber and give ions. Electric charge on the oil droplets was obtained or was acquired by collisions with the gaseous ions. See, the X-ray ionize air inside the chamber. When they ionize the air inside the chamber, you get ions. Now, by colliding the oil droplets with these gaseous ions, the charge on electron, the charge on oil droplets was acquired. Okay. And based on the charge that was determined, based on the charge that was present on the oil droplets that was determined, he proposed that it is a Q is equal to N into E, where Q is the charge on oil droplets is equal to the integral multiples. Here you have to take positive integer. Integral multiples of the electrical charge, nothing but the charge on electron. So this is an important relation. The charge on oil drops was determined to be 1 into the charge on electron, nothing but 1 into 1.602 into 10 power minus 19, or 2 into 1.602 into 10 power minus 19 coulombs, or 3 into E, the charge on electron. Okay. So this is all about the Millikan's oil drop experiment. Based on the rate of falling of the oil droplets, he could get the mass of the oil droplets. And the electrical charge on oil droplets was acquired by colliding these oil droplets with the gaseous ion. Now the ions are in fact obtained from the ionization of air inside the chamber using the X-ray. So taking this into account, he could actually determine the charge on oil droplets, and he found that the charge on oil droplets is integral multiples of the electrical charge. Q is equal to N into E, where N takes up the values 1, 2, 3, and of course, so on. Okay, so this is about oil drop experiment. See, I told you that the E by M ratio of cathode rays, the specific charge of cathode rays is independent of gas taken in discharge tube. But you know, in case of anode ray, you know, cathode rays consist of negatively charged electrons, whereas anode rays consist of positively charged protons. Electrons move from cathode to anode, whereas protons move from anode to cathode. In case of anode rays, you know, the specific charge E by M ratio depends, see the difference, depends on the gas taken in discharge tube. So this is the basic difference. Because you know, anode rays are obtained by the ionization of the gas taken in discharge tube. And they'll all be different. In fact, cathode rays are also formed in the discharge tube, but they'll all be same irrespective of the gas, whatever is taken. Whereas in case of anode rays, you know, E by M ratio depends on the gas that is taken in the discharge tube. Okay. Next. You know, see, let us now go for atomic number and mass number. Right. Now coming to this, as I told you already, that in general, an atom or a nuclide is represented this way, where X is the symbol of the element, Z, of course, is atomic number, and A is mass number, right? See, this atomic number can, of course, be given as equal to the number of protons present in the nucleus of an atom, or else the number of electrons of course in a neutral atom. If it becomes an ion, of course it will be different. But in case of a neutral atom, the number of protons is equal to the number of neutrons. Now coming to the mass number, it is equal to the sum of protons and neutrons. Nothing but the number of nucleons. Now finally, the number of neutrons can be given as A minus Z, because A is P plus N minus, of course, this Z is a P. Cancel out these two and you are left with N. So it is the number of neutrons. Now let us go for isotopes, isobars, isotones, isodiaphers, etc. Okay. First of all, what are isotopes? Isotopes are, of course, the nuclides having same atomic number but a different mass number. Okay. Let me give you an example that makes everything clear. Okay. Hydrogen has 3 isotopes. The first one is called protium. This is deuterium. And then there is something called tritium. Okay. Protium is also called ordinary hydrogen. Deuterium is called heavy hydrogen. And then tritium is called radioactive hydrogen. Okay. Now check out the number of electrons, protons, and neutrons in these 3. Coming to the number of protons in this, of course, even the number of electrons, 1, 1, isn't it? Because number of protons is equal to atomic number. Even the number of electrons is also equal to atomic number. Then the number of neutrons is 1 minus 1, that is 0. Coming to the number of electrons, In deuterium, even the number of protons, of course, is the same. The number of protons or number of electrons is equal to atomic number, nothing but 1. Coming to the number of neutrons, this one. Then coming to the number of protons, electrons, and neutrons in tritium. Look at this. You know, these three have got the same atomic number. But see, the mass numbers are different. And see, they have the same number of, you know, they have got the same number of protons, same number of electrons, but different number of neutrons. And see, because they have actually got the same number of electrons, their chemical properties are also the same. You can say at least similar. Remember, the chemical properties, nothing but the reactions in which they participate depend on the number of valence electrons. Of course, they've got just one electron that will be there in the valence shell or the last shell, because the electronic configuration of hydrogen is 1s1, right? So because they have got the same number of electrons in the valence shell, they exhibit similar chemical properties. But you know, because they have got difference in mass, their physical properties are different slightly. Let me give you an example. You know, if you consider the boiling point of water, which has got ordinary hydrogen, it is 100 degrees centigrade. Whereas if you consider the boiling point of heavy water, deuterium, which has got, I mean, deuterium oxide is heavy water, which has got heavy hydrogen, nothing but deuterium. See the boiling point, 101.42. The boiling point of heavy water is 101.42. Okay. So that is how they differ in their boiling point. They also differ in radioactive property. Okay. Let me tell you. Okay. So isotopes are those which have same atomic number but different mass number. They have got the same number of protons, same number of electrons, different number of neutrons. They exhibit similar chemical properties, differ slightly in their physical properties, and of course, differ in the radioactive property. Let me tell you what radioactive property is all about. You know, tritium is the lightest radioactive isotope. It is a beta emitter. I mean, it emits beta rays, which consist of beta particles. Let me show you that. You know, beta particles are nothing but fast moving electrons. This is the beta particle. Nothing but a fast moving electron. But you know, the interesting part is this electron is not the one that is revolving around the nucleus. It is not an extranuclear electron. Don't get confused with the electrons that are revolving around the nucleus. No, this beta particle is a fast moving electron, but you know, this has come from nucleus. It has come from the nucleus. But how? When a neutron present in the nucleus disintegrates, you get proton, electron, and a neutrino. Now, this electron that has come from a neutron is called beta particle. See, it is not something which is revolving around the nucleus. It has come from neutron. Where does the neutron reside? It resides in the nucleus. The neutron in the nucleus, when undergoes disintegration, you get proton, electron, and this is neutrino. It has no mass, no charge. I mean, negligible mass and negligible charge. What do you mean by radioactivity? Emission of, the spontaneous emission of alpha, beta, or gamma rays from unstable atomic nucleus. The unstable atomic nuclei. I mean, when they have much more neutrons than the number of protons. Say, for example, uranium. Uranium 92, 237 or 234. See, they've got much difference in the number of neutrons and that of protons. As the number of neutrons goes on increasing, the nucleus becomes more and more heavier. And at one stage, it undergoes a spontaneous emission. I mean, spontaneous disintegration to emit alpha, beta, or gamma rays. That is what is called radioactivity. Alpha rays consist of alpha particles. I told you that alpha particles are nothing but helium nuclei. Beta are nothing but fast moving electrons. Gamma are simple electromagnetic radiation. We call them gamma rays. Alpha rays consist of alpha particles. Beta rays consist of beta particles. Of course, gamma rays, they don't consist any particle, but they are the electromagnetic radiation. We'll discuss about different types of electromagnetic radiations later. But for now, you just remember that tritium is a beta emitter. Let us balance this now. 2 minus 1 is 1. 3 plus 0 is 3. Right? So this is about the isotopes. See, the element with the maximum number of isotopes is 10. Tin, nothing but stannum. It has 10 stable isotopes. Okay.